Man, it is a beautiful day in the neighborhood to learn about floating point numbers. A floating point number is basically a number with a decimal, like 34.5. Would you look at that? So to start, computers' floating point numbers are stored as a mantissa, which is the decimal part of a common logarithm, and an exponent. So it's really similar to how you write a number in scientific notation, if any of you guys remember that. 123.45 could be stored as something like 1.2345 times 10 to the second, or 12.345 times 10 to the first. Cool. Although the computer will use base 2 instead of base 10. That, just to know on the scientific notation thing I just said. But we already covered that stuff, so I'm not sure why I mentioned that. Probably because this is a tutorial. Anyway, floating point numbers can often be imprecise. There's a lot of numbers out there floating around that can't be stored with perfect accuracy in a floating point number. But computers are modern day heroes. It'll store pretty freaking close to the number you expect. Swift has two floating point number types, a float, which is a 32-bit floating point number, and a double, which is a 64-bit floating point number. It's pretty interesting though, because the different bit sizes of float and double don't determine a simple minimum and maximum value range as they do for integers. Instead, those bit sizes determine how much precision the numbers have. Since double is a 64-bit, it's going to be more precise than floats, meaning it's able to store more accurate approximations. First trivia of the day. True or false? The default inferred type for floating point numbers in Swift is double. Cue the Jeopardy music. True. You are so correct. Double is the default inferred type for floating point numbers. I really feel like I'm jargon bond strangle here because all this jargon without code is, what good does that do? So let's do let personality equal 1.1, which is explicitly double, but also low rating for personality. And let attractiveness be a double equal 1.1. This is explicitly declaring a double. And let wealth be a float equal to 100.3. Very wealthy, winky face. So all of the same numeric mathematical operators work on floating numbers too. The ones that I showed you previously, except for the remainder operator, but who's going to use remainder operator on floating point numbers anyway? Just to show a quick example, plus 123.0. Wow, wonder what that'll be. I don't know. Math's kind of hard to do in the head, The fact that floating point numbers are inherently imprecise is a pretty important difference from integer numbers that you should probably write down, keep in mind, or tell somebody no. Or maybe you could just share this video and put that as the caption. I'm just brainstorming here. But to prove that point, let's do personality equals attractiveness. Did I spell that right? And let's print personality and attractiveness are the same, which is, I don't know. Yeah, I don't want to comment on that in the literal of those two words, but as far as the values go, these are equal because 1.1, it's all good, everything's good. Personality and attractiveness were both given a value of 1.1, so the code is good, but I wouldn't date this chick. Let's add a 0.1 to personality. So what do you think the if statement will print out now? I guess I should probably write it and then ask you that question, so you can get a visual of what's going on in these parts. Personality plus 1 is personality point 1. I could pull up the console here. 1.2, blessings. So if we did personality plus 0.1 equal to 1.2, because we see that right here, let's print personality plus 0.1 is equal to 1.2. Whoa, what is going on here? So we see the first print statement, but where the heck is this one? 1.2 is equal to 1.2, right? Well, sometimes it is and sometimes it isn't, I guess. Floating point numbers, am I right? Many numbers can't be represented exactly in a floating point number, such as 1.2. So the computer stores a super duper 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 close approximation to 1.2. So when we add 1.1 and 0.1, the result is actually something like 1.200000000000001, and that value that we stored in a literal 1.2 is something like in this guy is something like 1.19999999999, you know, which is pretty close. So Swift is pretty smart though. It'll round both of those to 1.2 when we're printing them, but they're technically not equal. So that's probably why this guy is not running. The moral of this story, the moral of this book, this novel that we're unfolding is don't use floating point numbers for values that need to be exact. Since we haven't done a challenge since Vietnam, since we haven't done a challenge since like Vietnam, how about you grab a pen and a paper and try to figure this little brain teaser out. What is the binary? Should I type this too? What is the binary man, didn't even do a comment. Command / representation of -1 using an 8-bit signed integer. And if we took that same bit pattern and interpreted it as an 8-bit unsigned integer, what would the value be? Leave the answer in the comments below, and I'll see you in the next video. Subscribe, like, follow, share, subscribe, content, love, beautiful, sacrifice, #. See you then.